Introduction to Xray machines. Xray machines is a device that uses high-energy radiation to observe the insides of an object without physically altering the exterior of the object by opening or damaging it. Usually, when mentioning Xray machines, people would usually equate it to its usage in the medical fields. Though, generally speaking, it is also a device that is used for security screening at the airport, art and archaeology, astronomy, material analysis, forensic, and many more. Historically, X-ray was discovered by Wilhelm Röntgen in 1895 while experimenting with cathode rays using a Crookes tube. Unexpectedly, he noticed a fluorescent screen and deduced it to be a new type of invisible radiation and named it X-ray. His discovery charted a new course of research to open up regarding radioactivity, electron theory, and atomic structure. Continuing the discovery of X-ray, it is now a very important knowledge that is used to a certain degree, such as observing how materials behave under stress, detect hidden flaws, improving manufacturing techniques, and support the development of better and stronger materials.
These are our group members.
Now, I'm going to talk about the real-world implementation of Xray. The first one is medical diagnostic, security screening, and also non-destructive training. For the first one, Xray technology is one of the most essential diagnostic tools in modern medicine. From conventional radiography to advanced digital radiography and CT scans, Xray machines are used to diagnose fractures, infections, and internal abnormalities. For the second one, which is security screening, airports and also border control use X-ray scanners to detect concealed items in luggage or cargo. The systems are tailored for high throughput environments and can distinguish between organic and inorganic materials. The third one is non-destructive training. So for industries like aerospace and manufacturing, the non-destructive training has become an essential aspect of quality control and also material research, enabling the researchers to assess the internal structures of materials without damaging them using the X-ray. These are the example of the real-world implementation of X-ray as I mentioned before. There are CT scan machines, X-ray machines, and also how the non-destructive training works, and then how the security screening always look like in airport or at place it's supposed to be.
Now for potential benefits and challenges. Let's start with benefits. Scientific instrumentation enhances precision in data measurement and analysis, which is essential in getting accurate and reliable results. This is especially useful in research, clinical diagnostics, and industrial processes. It also increases efficiency and speed in experiments, allowing researchers to conduct more trials in less time with less effort. Instrumentation supports automation in industries, which not only speeds up production but also ensures consistency in results. This is one of the key reasons it's widely adopted in fields like pharmaceuticals and manufacturing. Another major benefit is that it reduces human error. With less manual handling of data or equipment, the chance of mistakes is significantly lowered. Now let's move on to the challenges. One big challenge is the high cost of advanced instruments. These devices can be expensive to purchase and not every institution can afford them. Another issue is that they require specialized training. People need time and expertise to operate these instruments effectively, which might limit accessibility. There is also the complexity of calibration and maintenance. These processes can be difficult and may require professional support or regular servicing. Lastly, data overload and interpretation issues are common. Modern instruments collect large amounts of data, and without proper system or skills to interpret it, valuable information can be missed or misunderstood. Future developments and innovations. In the future, we can expect exciting advancements in scientific instrumentation. One of them is AI-driven instrumentation for real-time data correction. This means instruments will be able to detect and fix errors as they collect data, improving accuracy without needing constant human supervision. Another development is miniaturization for portable use. Instruments are being designed to be smaller and more compact, making them easier to carry and use in the field, especially helpful for environmental monitoring, mobile apps, or emergency situations. We will also see more integration with IoT for real-time monitoring and alerts. This allows instruments to connect to networks and send data instantly. For example, sensors in a lab or hospital can alert users in real time when something goes wrong. Lastly, there's a growing focus on green instrumentation, low power, and eco-friendly designs. These instruments are made to consume less energy and use sustainable materials, which helps reduce environmental impact and support long-term sustainability in science and industry.
How an X-ray machine works. Character F element. Function is send electron towards a target metal. And second, anode as target metal. Function attach high energy to achieve high radiation intensity. High voltage sources. The function is accelerate electron toward the anode. Lastly, glass or metal tube. The function is maintain a flow of current for electron emission. And lastly, cooling system. The function is remove heat generated from the anode due to electron impacts. The process that are produced by X-ray. First, produce when electron knock out initial electron, K or I shell. Second, electron from higher shell drop into the vacancy, releasing X-ray with specific energy. Next, scientific instrumentation concept. First, bright slow diffraction used to study crystal structure. The formula is 2 sin ND equal to N lambda. This application to X-ray crystallography to reveal the molecular and atomic structure of solidification of X-ray in scientific field. First, X-ray imaging as medical. Concept involved is absorption contrast. The explanation is diagnostic tool in medicine. Bone absorb X-ray more than soft tissue, creating contact image. Second, material analysis (NDT). Concept involved is penetration rate. The explanation is non-destructive testing to find crack defect inside metal parts used in engineering and aerospace. That's all for me.
X-ray machines are essential tools used primarily to detect weapons, explosives, and contraband in luggage or on individuals, especially in high-security areas like airports and public venues. They work by emitting X-rays that penetrate objects. Denser materials absorb more radiation and appear brighter on the resulting image. Detectors capture this internal image for analysis, allowing trained operators to identify suspicious items. There are various types of X-ray systems, including baggage scanners, body scanners, and large cargo scanners for vehicles and containers. Advanced features like dual energy imaging used to color code different materials. 3D CT scanning and AI-based threat detection further enhance their accuracy and efficiency. Operators play a vital role in reviewing and interpreting the images to ensure safety. Despite using radiation, these machines are shielded, emit very low doses, and meet strict international safety standards. Beyond security screening, X-ray machines are widely used in industrial building inspection, where they reveal internal cracks and defects in pipelines, aircrafts, and construction components without damaging the parts. In archaeology, they allow researchers to examine the internal structures of fossils, mummies, and ancient artifacts non-destructively, aiding discovery while preserving priceless materials. This versatility makes X-ray technology indispensable across security, industry, and scientific research.
Conclusion for X-ray machines. In summary, X-ray technology has evolved from simple medical imaging into a powerful tool used in science, engineering, security, and industry. We've seen how scientific concepts like attenuation, phase contrast, and tomography enable detailed analysis of internal structures. Real-world implementations from airport scanners to analyzing metal microstructures shows just how valuable this technology is. While it offers clear advantages like precision and non-destructiveness, we must also consider issues like radiation safety and equipment cost. Looking ahead, innovation will continue to improve resolution, reduce exposure risks, and open up even more groundbreaking applications.